In the first part of this chapter, we really looked at carbon, and now we're going to look at when we have heteroatoms. So we have atoms that have things other than hydrogen and carbon. What this does is it starts to line up some of our other things that we're looking at in terms of electronegativities. So I always like to draw out our electronegativities, showing fluorine is the most electronegative, oxygen, chlorine, nitrogen, sulfur, and bromine, carbon, phosphorus, selenium, iodine, and then boron, silicon, these kind of intermediate elements over here we can draw down, and we're typically not going to use some of those arsenic, tellurium, astatine. Those aren't really organic compounds, but we will look at boron a lot. That's an interesting chemical that sometimes gets involved in these. But we're right now going to focus on these functional groups on the top row of the periodic table and looking at nitrogen, oxygen, and then also the halogens as well. And you'll see that these oftentimes will lead to changes in electronegativity difference because we're talking about carbon attached to nitrogen or oxygen or any of these other elements, fluorine, chlorine, or bromine. They're going to set up these electronegativity differences, and that's going to cause interesting chemical reactivities and processes to occur. Here's a list of some of the various compounds containing halogens, nitrogens, and oxygen as those heteroatoms. And we'll go into the first one is the alkyl halide, where we have this R group. Remember that R group is some type of organic chain of carbon, and it's attached to X. So X is commonly used to refer to halogens, which would be fluorine, chlorine, bromine, iodine. And these elements attached here's an example, they'll have these three lone pairs because of where they are in the periodic table. For their complete octet, they would have these three lone pairs. And the example here, bromomethane, and we just have a methyl group and then the bromo group. And you can see the three-dimensional structure. Since the bromine has these three lone pairs, it's kind of on the end, and then it's attached to a carbon that is tetrahedral in shape, sp3 hybridized. So we have those four sp3 orbitals, using those to make bonds to 3 oxygen and 1 bromine. Alcohol is the next functional group. We have a chain of carbons attached to an OH group. The oxygen has those 2 lone pairs, and you can see this bent orientation that's shown in the example for methanol. Here, the carbon is tetrahedral, attached to 4 things, sp3 hybridized. The oxygen is also sp3 hybridized, and we have 2 bonds, and then the lone pair, which are not being shown in this 3D structure, are up on top, causing this bend here, and that is also referred to as a hydroxy group. So here, the halo group is considered, the X is typically used to suggest that any of these might be involved in that bond. That's a halo group, hydroxy group, OH. And then the next one we'll talk about is the alkoxy group. That is also referred to as, the type of the compound is an ether, where we have 2 chains on either side of the oxygen. So you can see this is within that chain. This oxygen here, 2 lone pair. We still have a bend because this is still sp3 hybridized, and those lone pairs take up room on the top of the element. So dimethyl ether here, there are 2 methyl groups. That's the dimethyl, and then the ether is named in the middle. You can see here the 3-dimensional structure, sp3, sp3, sp3 hybridized, and then the lone pair on top causes to have a bent shape around the oxygen, and still tetrahedral around the carbon groups. Again, that is referred to an alkoxy group. An amine functional group, where we have a R group, a chain carbon attached to a nitrogen. You can have 1 carbon attached, you can have 2 carbons attached, you can have 3 carbons attached to the same nitrogen, and even 4, and we'll look at that in a second here. So this is the shape. Remember, the lone pair, typically if it does have a lone pair, it's going to have this trigonal pyramidal shape. Pyramid, because it has, you can kind of see that comes down, and it's not planar, it's not flat, it's got a pyramidal shape. So this is an amine functional group. That NH2 group is referred to as an amino group. So you might have heard of an amino acid because they have this group on them. Thiols are where we add sulfur, so this carbon group. And this is an analogous structure to oxygen. You'll see it has the lone pairs, it has the hydrogen on the end of it. It's got a similar structure in terms of the bent shape because the lone pairs on the top. So really similar types of shapes and structures. You can see the oxygen's obviously a smaller atom, so this is represented a little bigger. This group is called a mercapto group. You may have heard of beta mercaptoethanol, perhaps. When we run protein gels, we have to use that to denature our proteins, and it kind of stinks. So if you've also been in a hair salon where they're doing perms, for example, that's kind of that stinky flavor smell that you get is the mercapto smell. So these thiols and these sulfur-containing compounds are typically pretty smelly. Another sulfur-containing group that's an analogous group to these ethers with oxygen is the sulfide group. So thiol group versus a sulfide group. This is where it's within a chain, and you'll see that this has again a bent shape, and it has the lone pair on the top, so it is bent, and the carbons are still sp3 hybridized. The sulfur is still sp3 hybridized, so the carbons are tetrahedral, but the sulfide, because of the lone pair, is bent. This is an alkyl thiol group. So alkyl thiol group is that group name. Next, we're going to look at some groups where just kind of built into different types of compounds. Here's a diethyl ether. On the other page, it was dimethyl ether, and you can see the chains are a little longer. Similar common types of organic solvents will be diethyl ether. Maybe you're using this in the lab right now. The hemibrevetoxin B. Hemibrevetoxin is a toxin produced by, it's an aquatic neurotoxin. It's actually in the red tide. You might have heard of this. It's a dinoflagellate known as Carenia brevis, hence the name breve. The brevetoxin. So this is a part of that. Some of these are longer chains, but it's a neurotoxin. But there's also a mechanism for the synthesis of this. So this can be, even though it is a biological compound developed by a biological system, it can be completely synthesized in an organic chemistry lab. Some of the interesting characteristics of this are these built-in oxygens here, and this is part of the important part of the ability to make this. These big long rings through these oxygens are an important part of that process. So these are ethers within that structure. Next, we want to classify these alcohols and halides so that we can start talking about them and understanding the types of chemical reactions that might occur depending on if they are classified differently. So we're going to look at typically if we're looking at alcohols and halides, we're looking at the carbon that they're attached to. If we're a halide, right, we're bromine, chlorine, iodine, those are going to be only attached to that carbon. And that carbon is going to dictate if the halide is a primary, secondary, or tertiary. So you can see here, this carbon that is attached to the halide is attached to one other carbon and just two hydrogens. So this is a primary halide. And if it were this Z were instead a hydroxyl group, it's the same thing. So this carbon is attached to one, and that's a primary alcohol. If we move over here, this carbon's attached to two other carbons. So this Z group, whether it's a halide or an alcohol, it would be a secondary because there are two carbons attached to the carbon that's attached to the functional group, or a secondary alcohol. And finally, we get to the tertiary alkyl halide where it's attached to three things. So this is going to be an important, something that is important for you to be able to classify these different alcohols and halides, and something I'm going to ask you to do. Here's just an example of a long chain of carbon with various different types of alcohol and alkyl halides. So here is an example of a secondary chloride. You can see that carbon that it's attached to is going to define that, and it's going to be attached to one carbon and two carbons, and therefore it's a secondary chloride. The second example, this carbon that the hydroxyl group is attached to 3 other carbons. Therefore, it's a tertiary alcohol. So again, based on that carbon and the state of that carbon's bond, not necessarily the state of the oxygen. Okay, here on the end of the chain, we have just one carbon attached to the carbon that's attached to the hydroxide group. So it is a primary alcohol. So that's how we define those. Now you get a chance to practice doing this. I'd like you to classify these. Make sure that you write these down in a notebook that you're going to bring to class or include in anything that I might ask you to do later. So I will ask you to provide the answers for these later. So please do write these down, bring these to class. I also wanted to just talk about classifying amines as well while we're kind of classifying things. Nitrogen-based compounds are a little different than the halides and the alcohols because they can attach to more than just one thing, right? If we have an OH group, that can really only have one attachment point. It only has one spot open for attaching. But nitrogens can have multiple groups attached to it. So if we're a nitrogen and we're only attached to one carbon chain, then it's a primary amine. If it's attached to 2 carbon chains like we see here, we have one on the right side, one on the left side, and a single lone pair and a hydrogen, that's going to be a secondary amine. So it's based on the number of carbon chains it has. For a tertiary amine, it's attached to 3 carbon chains. And then a quaternary amine, it would be attached to 4 carbon chains. And notice that quaternary amines are always going to be positively charged. Because remember, if we're looking at formal charge, nitrogen in the valence shell will have typically 5 electrons. If we look here in this tertiary amine, it's got 2 of that it's not sharing alone here. So that's 1, 2. There are 2 in each of these bonds, but it only gets to count 1 electron in each of those bonds. So we go 1, 2, 3, 4, 5. So 5 valence electrons, 5 bonded electrons. That gives it no charge. But over here, if we typically have 5 valence electrons and then 1 electron from each of these bonds, that's only 4 electrons. So it lost an electron from its valence shell. It's donating these to some other molecules or atoms, so that therefore gives it a positive formal charge associated with that nitrogen. So it's a little bit different convention for classifying amines than it is for the halides and the alcohol groups. Same with the last learning check slide. Please write this down. Bring your answers to class. I just want to verify that you're doing the activities I'm asking you to do while we're doing these virtual videos here, and then just to check to make sure we're on the same page. Bring that to class and we'll cover that material at that time. So that wasn't all of the compounds we're covering. Now we are covering different compounds that have carbonyl groups in them. So the carbonyl groups is this carbon double bonded to oxygen. So the previous examples in that previous table, those were typically, you noticed, perhaps just single bonds. Now we go from an sp3 hybridization state for carbon to an sp2 hybridization state. Remember that other p, that we go from an sp3 to an sp2, that p orbital is being used to create this pi bond, right? The p for the pi that is happening here. So the carbon is sp2 hybridized, the oxygen is sp2 hybridized, and then we also, that shape is associated with that hybridization change. We now have a trigonal planar shape. There are, again, electronegativity differences between carbon and oxygen. So we'll have a partial positive charge on this carbon and a partial negative charge with this oxygen. And this really allows a lot of chemical reactions to happen with this functional group. So there are different functional groups that contain that. There are 1, 2, 3, 4, 5, 6 of these that we're going to cover right now in terms of the carbonyl group. The first is the aldehyde, and that's where that carbon R group, this is on the end of a chain. So you can see an example here where we have the condensed structure, the example, and then the 3-dimensional structure. So this carbon, you can see that carbonyl group is on the end of a chain, that hydrogen's at the end, and then we have a carbon-based group. So compare this with the ketone, very similar, except for the difference here is that instead of on the end of a chain, this carbonyl group is in the middle of a chain. So that's the difference between an aldehyde at the end and a ketone where that's in the middle. Next, we're going to go to a carboxylic acid. And now the difference here is that it's more like an aldehyde, but instead of a hydrogen here, we've replaced that with a hydroxyl group. But this is all one big functional group. So don't think this is an alcohol group and that's a carbonyl group. You wouldn't separate those out. Since these are directly attached to each other, this carbon is directly attached, this creates a special system that has special chemistry involved. And you may notice from the previous chapter, in chapter 2, this group is really acidic. That's why it has the carboxylic acid component. It's pretty acidic because of this structure, really because of the conjugate base that's formed, that's stabilized because of this structure. So you can see over here in the three-dimensional, again, trigonal planar, and we have this at the end. Now, it looks similar to an aldehyde, except for we've replaced that hydrogen with a hydroxy group. Next is the ester compound. Again, similar to a carboxylic acid now, but we've changed. If we look at the difference, is instead of this hydrogen and then on the top, on the end of there, now we have a carbon structure. So the ester, we have turned that into a carboxylic acid. Now we've added a carbon group on the end. It doesn't have to be one, it could be 3 or 4, it could be a longer chain, but it just has to be at least one. So that's the difference between a carboxylic acid and an ester. Now we go to an amide functional group. Notice the IDE versus the INE. So if we're talking about an amine, that is different than an amide. And the amide is that we have this carbonyl group directly adjacent to the nitrogen that's being attached. So here's an example of that. It looks similar to the carboxylic acid, except for now we have instead of an OH group, we have an NH2, for example. And this could also have other attachments with carbon, but this is minimally what we would have for an amide functional group. You're just looking for that double bonded oxygen to carbon and the carbon directly bonded to a nitrogen. So that's an amide functional group. Finally, we're going to talk about an acid chloride, and it's very similar to a carboxylic acid, for example, that we have that end group. Here is just that carbonyl group attached to a chlorine. So you would see it typically written out, the condensed structure. So the COCl. Notice that these are typically the COOCH3, COOH. You'll note this is how these would typically be written by convention for the condensed structure, and then this is what these functional groups would look like. So those are the overview of the compounds that we'll be talking about in this chapter for the carbonyl groups. And you should know these. These are things that I would like you to, I don't ask you to memorize a lot of things, but these names and what the basic structures and to be able to identify those are things that I do want you to know for this class. So a really fun exam or quiz question for me to ask is for you to, I'll give you a complex structure of maybe some type of drug like this atenolol or donepezil used to treat Alzheimer's disease or high blood pressure. And then I'm going to ask you to identify all of the functional groups. So I want you to make sure when you're doing this that you are identifying the full thing. So a lot of times people will make the mistake of, oh, here's a nitrogen, so this is an amine. But notice that nitrogen is attached to a carbon that's directly attached to the carbonyl group. So this is actually an amide functional group. So you can't parse them apart so much that you miss some of the whole of the functional groups. But here's an example, and just this is all kind of written out for you and identified. So again, this is an amide functional group, not just an amine. We have an aromatic ring. Talked about that. Here's an ether within that ring or outside of that ring. Alcohol. Here's an amine functional group compared to an amide functional group. A few ethers, a ketone because this is in the middle of a chain, aromatic ring. Here's another amine and another aromatic ring. So these are things that I want you to start to be able to identify and find within different structures and properly name. Something else you should be able to do and you should practice doing is you should be able to draw the structure of a compound where I give you the chemical formula, I'm telling you what functional group is in there, and then you should be able to draw that out. So that this is something else I'd like you to do. So take you some time, grab a piece of paper and write down your answers for this, and we'll check this in class the next time we meet. And this is a good place, I think, to stop for this kind of shorter video on this next part for chapter 3. And then in the next section, so I've introduced those functional groups. You should start to, again, learn those and know what those are and be able to identify those and draw those out. And next, we're going to talk about some of the intermolecular forces and how those different functional groups play with those forces to have different reactivities and different properties.